Greetings, my dear viewers. Today we'll be covering an important component in classical physics, kinematic equations. So let's begin by understanding what these equations are. Basically, these kinematic equations are a set of fundamental equations to describe the motions of objects in one dimension, typically along a straight line or linear motion. These form an integral part in classical physics and are not only used by physicists but in various fields around the globe. I'll just begin with the equations right in. Let's write down the equations on the board. The simplest of them all is v is equal to u plus at, which is final velocity is equivalent to the sum of the initial velocity and the product of the acceleration and the time. The second equation is v square is equal to u square plus 2as, or the final velocity square is equivalent to the initial velocity square plus 2 times the acceleration and the displacement. The third equation states that displacement is equivalent to the initial velocity multiplied by the time plus half times the acceleration times the time square. The fourth equation removes acceleration and states that the displacement is equivalent to the product of the initial and final velocities summed and the time whole divided by 2. These equations are also called as the SUVAT equations since they play with the displacement, initial and final velocities, acceleration and time. Now let's solve some examples. We have a ball with initial velocity 24 meters per second once kicked. It then continues its journey with a deceleration of 2 meters per second square. Can you tell me how this deceleration occurs? Well, if you got it right, well done. The friction on the ground simply causes this deceleration. It continues, and after its enjoyable journey, it comes to a stop with a final velocity of 2 meters per second. And now, the grand question that the ball tries to hide and we try to uncover is the time taken in this enjoyable journey. So which equation should we use here? Well, it's rather simple. We should use v is equal to u plus at. The choice is reasonable because we have v, the final velocity, u, the initial velocity, and a, the acceleration. And we have to find t or time with the generous assistance of our brains. You may want to pause the video and try to find the solution. Okay, let's solve it together. We know that v is equal to u plus at, and if we substitute the values, we have 0 meters per second is equal to 24 meters per second plus minus 2 meters per second square times t. And if we move the q24 to the left hand side, we have minus 24 is equal to minus 2t because 24 deserves some change after walking to the other side, and the change is not always positive, right? Now to make t 24 and 2 happy, let's make them positive. So we have minus 24 divided by minus 2 is equal to t, and finally we give t a value which it had been patiently waiting for as 12 seconds. Notice how in classical physics it can only take 12 seconds and only follow a particular path to reach its destination, which we'll look at in another video. Now let's look at another problem. So here we have an astronaut who was jumping to join us in physics. This man has an initial velocity of 2 meters per second. Being an astronaut, he should know his acceleration, and he finds it out to be 3 meters per second square. He continues his walk, and after 3 seconds, he stops abruptly. He stops and starts crying loudly, explaining that he did not measure the displacement. Can you help him? Yes, of course you can help him, and let's help him together. First, let's clear the screen for some math. What we have are the initial velocity of the astronaut, which is 2 meters per second, the acceleration, which is 3 meters per second square, pretty fast, and the time, 3 seconds. Since we have to measure the displacement at the initial velocity, acceleration and time given, we shall use the third equation on the screen, which is s is equal to ut plus half at square. If we substitute the values, we have displacement is equal to 2 times 3 plus half 3 times 3 square. This simplifies to 6 plus 1.5 times 9. Now note that 1.5 times 9 is equivalent to 3 times 9 divided by 2 because 1.5 is the half of 3. 3 times 9 is 27 and 27 divided by 2 is 13.5. We therefore have S or displacement is equal to 6 plus 13.5. And therefore, the astronaut was displaced by 19.5 meters in only 3 seconds, which is very fast. Let's hope he was actually walking. Okay, now let's consider another one, and let's test if your brains are still functional. We have a ball back in this puzzle. So an intelligent human decides to throw this ball with an initial velocity of 3,421 meters per second into the air. The acceleration due to gravity is 9.81 meters per second square because he's not throwing it on Mercury or Venus or Mars or Jupiter or Saturn or Uranus or Neptune or Pluto or on the moon, but on the Earth. It takes the ball 3,563 seconds to reach the highest. And in 2 minutes or 120 seconds, can you tell me the final velocity of this particular orange ball? Pause the video and try to solve it. Remember, no calculators. If you solved it in a matter of seconds, well done. If you solved it in 2 minutes, no issues. If you require more than 2 minutes, all the best from my end in the future of your physics journey. And if you got it wrong, well done again. The answer to this problem is simply 0. So when the ball is first thrown, it has a particular initial velocity. Then it continues for some time in history and slows down and down in speed, at which it goes up due to the deceleration due to gravity and eventually stops, which is its final velocity. Then, after a small time in history, it again falls down with 0 initial velocity and ends with a high final velocity. This was a conceptual question, so there's absolutely no issues if you got it wrong or couldn't solve it. We'll work on it together. Now to make your life easier, we'll conclude this video by reforming these equations into free fall and upward motions so you don't need to face the same issue again. Let's start with free fall. The first equation would transform into final velocity is equivalent to the acceleration due to gravity multiplied by the time. The initial velocity would be 0 as we discussed before. A would transform into acceleration due to gravity, g and t would remain as time. The second equation would change its physical appearance into the final velocity squared is equivalent to the product of acceleration due to gravity and the displacement multiplied by 2 again. A is nothing but acceleration due to gravity and u would be 0. The third equation would transform as the displacement is equivalent to the product of the acceleration due to gravity and time squared divided by 2. The last equation would transform as the displacement being equivalent to the final velocity divided by 2 multiplied by the time taken. The initial velocity is 0, therefore it is not considered here. Presently, had embarked on the journey of transmogrifying the extant kinematic equations within the milieu of unimpeded gravitational descent. It becomes imperative to deliberate upon their application in the constant of ascendant motion, thereby invoking a comprehensive exploration of the principles that govern these distinct but intimately intertwined physical phenomena. Or basically, let's have a look at upward motion. Now in case of upward motion, the final velocity is 0 as we had discussed, and the motion and acceleration due to gravity are in opposite direction. Therefore, the initial velocity is equivalent to the negative acceleration due to gravity multiplied by time. The second equation would transform its skeletal structure to become the final velocity is equivalent to 2 multiplied by the product of the acceleration due to gravity and the displacement. The third equation also goes to the transformer machine to become displacement is equivalent to the sum of the products of the initial velocity multiplied by time and the half of the acceleration due to gravity multiplied by time squared. The fourth equation transforms to become initial velocity squared is equivalent to the negative of 2 times the gravity multiplied by the displacement. Here we conclude our exciting journey on the kinematic equations. If you have any queries or find even the smallest error in our video, please let us know in the comments below. Of course, there's a lot of physics yet to come. And if you want a specific topic, we'd be happy to hear you. And your feedback is welcome. So please spend a second in giving a short comment. Finally, this video was made with a lot of hard work and efforts. And if you found this valuable in any manner, please support us in any manner possible. Signing off, the Physics Simplified community by powershift.com.